Okay. Okay, so I'll just repeat this first part then. Machine learning. Great, what is machine learning? Describe like a suite of computational and statistical approaches that extract patterns from data. So these three types of machine learning. The first is unsupervised. Chris talked about doing clustering, right? That he's going to cluster all of your interests. This is one form of unsupervised learning. So unsupervised learning algorithms are about basically taking data and without any human supervision, without any human telling it, this is what I want you to learn, finding structure in the data, finding either groups of data or doing dimensionality reduction to reduce the data so that it's a more manageable type of data set. You mentioned having lots of features, so that's the type of thing we address. That's a relatively small part of machine learning. Most of what's going on in machine learning today is in supervised learning, which is based on, these models are require you to have training data. So you tell the algorithm, here's a small sample of things I want you to learn. Here are the covariates, here's the outcome, learn how to predict this outcome from these covariates. And the last area is reinforcement learning, which we're not going to talk about, is really an exciting thing that's going on in artificial intelligence and computer science today. I think there might be some there's certainly some relevance to like economics, but really reinforcement learning is somewhere in between these two approaches. And the goal is to learn a policy where the algorithm goes through some covariate space or whatever, some feature space, and when it does things correctly, it gets a reward. And so if you followed any of the exciting stuff from Google about playing Go, or StarCraft, or whatever, or Pac-Man, these are all reinforcement learning algorithms. I'm not going to talk about it anymore today. It's not really happening in computational social science yet, but I think in 5 or 10 years it will be. Great. So these are the learning goals. Gain an intuition for machine learning and how approaches differ from statistics. Gain familiarity with unsupervised learning algorithms. We're going to go through how you do supervised learning. What is the workflow of supervised learning? Because I think that's the thing that's most different from how you approach traditional statistics. If there's one thing conceptually and theoretically I want you to understand, it's this Blas-Variance Tradeoff. We'll talk about how to evaluate classifiers, gain some familiarity, that's supposed to be the supervised learning algorithms, and then lastly we're going to do a deeper dive into decision trees. And in the afternoon, Marcel is going to lead you through a hands-on pen and paper and then coding activity for how to use decision trees. Great. So, unsupervised learning. I think I already told you this. Yes. But does this thing work? Oh. All right. Great. So yeah, unsupervised learning is great for discovering clusters in your data. So I'm going to talk quickly about two different very common algorithms for discovering clusters in your data. It's also great for dimensionality reduction. So if you have an overwhelming number of features, very common in machine learning is that we have lots of data, and very possibly a lot of that data is crap. And the standard machine learning approach is to throw all of that data into the model and hope that the machine, the algorithm can figure out what stuff has structure and what doesn't. But there may be cases where you want to reduce all those covariates to a more meaningful set of covariates. And that would also be an unsupervised learning approach. And if we were to use those covariates for a supervised learning algorithm subsequently, that would be called feature extraction. And then the last thing is just like exploratory. When I want to look at my data and I have this overwhelming number of variables and I want to see how they're related or try and get some sense of what patterns are in my data, we might use an unsupervised learning algorithm to do dimensionality reduction to 2 or 3 dimensions, just so I can visualize what's going on and see if there's any things that pop out to me about what my data looks like. Okay, so let's start with clustering. So the goal of clustering algorithms is to put individual datums into groups by minimizing the distance between data within the same group. Does that make sense? Mm-hmm. So how do we calculate distance? So you can imagine that we have a n-dimensional covariate space, right? Where if I have 3 covariates, I'm in a 3-dimensional space, and if I have 5 covariates, I'm in a 5-dimensional space, etc. And so we need some way, if we can imagine our data points in this space, we need some way to figure out which data points are closer to each other. So the most common distance metric, which you'll see coming back to this over and over and over in machine learning, is the Euclidean distance, or sometimes called the L2 distance, right? And this should be pretty clear to you. This is like, the Pythagorean theorem distance here, right? We take, for each covariate in the feature space, we calculate the distance between it, then we square it, then we add them up, and we take the square root of the whole thing. Okay? That's the Euclidean distance. Right. Next one would be the L1 distance, or the Manhattan distance, right? And in the L1 distance, we do the same thing, except instead of squaring, we take the absolute value, so that we don't have any negative distances, and we sum them up. There are many, many other distance metrics that might be useful to you in different cases. One which is like very useful if you have a lot of discrete data is like the Hamming distance. So this is something that comes out of biology actually, where you might have sequences of nucleotides, and you want to see how many of these nucleotides are the same across my entire sequence of things. So I'll give an example of how I use that for something in a bit. But this is just to give you you will probably be using this 80, 90% of the time, but there are so many other distance metrics, and you would need to find out what's most relevant to your data. Okay, so the simplest, I would say, or most intuitive unsupervised learning algorithm is, so is this thing definitely recording? How do I know?
Because it has a red light.
Yeah, but is the microphone thingy working?
I'm not 100% sure.
Okay, whatever.
Just speak loudly.
That's Matt.
Yeah,
Okay.
should we go get Matt?
Yeah,
or-
that's Matt. Just keep
Okay.
going. Keep going.
Great. So k-means. So this is what I was telling you about, right? If we can imagine that we have two covariates here, we're in a two-dimensional space. So we have our raw data, and k-means, the first thing we want to do is initialize the centers of our clusters. And so there's probably a smarter way to do this, but there is a smarter way to do this, but the simplest way to do it is to pick random points in the covariate space. And also, shout out to my collaborator, Jia Hui, who Jenny and I and Jia Hui finished an encyclopedia entry 2 weeks ago, and Jia Hui furiously made all these fantastic figures. So she did this. And I also want to shout out to obviously Marcel, but also Alina, who helped prepare a version of this last year for something else we did at UCLA, and Pablo, who you'll hopefully get to meet next week, who is also involved in that.
That paper we produced is on the CCPR working paper series, so you can download it. And a lot of this material is covered on that paper.
Yeah. Okay, so back to k-means a second time. We are going to initialize centroids, right? And then there's a loop in k-means. Now what we're going to do is we assign, using our distance metric, we assign each data point to the nearest centroid, And that requires, of course, calculating the distances between every point and every centroid, right? Then we recalculate the means. So you take all those distances and you compute the average. And that's the new center of your cluster, right? And you go back between this step and this step over and over until you can no longer assign any data points to a new cluster. So in practice, this is minimizing the within cluster variance and maximizing the between cluster variance. Cool. Does anybody have any questions about that? Marcel.
Just make sure you speak into your microphone.
Okay.
That's the only thing. It's
Great.
working. It's fine.
Perfect. Okay, the next thing I want to talk about is hierarchical clustering. K-means you will produce these clusters, but maybe you want some gradated idea of how your data is clustered. Maybe there are different levels of organization in your cluster. And hierarchical clustering is a great way to look at that. So my background is actually in evolutionary biology and phylogenetics, and that's actually the field where these types of algorithms initially came out of. So again, like the idea of clustering sequences of DNA or lists of fossils or whatever to come with a taxonomy of species is where these algorithms are from. So there are a couple different types of approaches for clustering. Some of them start from clustering from the bottom up. Some of them start from clustering from the top down. The one here is an algorithm, if you're interested, it's called neighbor joining, or UPGMA. And in some ways, it's very similar to what we did in k-means. Basically, we take every data point and we calculate some distance metric between every data point, and we pair them, right? So this is a recursive algorithm. So the first step, I take every data point, I find its nearest neighbor, I guess, and I bundle them together. And I do that for all the data points, and now I have a bunch of two-pair bundles. Then I take all the bundles, and I bundle them to their nearest neighbor, and I keep doing this until I have a single group at the top. So this is a recursive algorithm, and this is what you get. And this can be, well, I'd say, like, I'm going to talk about hyperparameters later, but one of the things you need to do as a researcher is decide at what level of organization you want to cut the tree to find the clusters that are most meaningful to you. So this is a project that I was doing where I had 120,000 metal bands, and they all described what genre they played completely differently. They had open strings. So they were like, this one says I play death metal with grunge influences or whatever, and this one is brutal, blackened, brutal, yeah, technical death metal, whatever. So I have all these strings, and I want to get kind of a more clear idea of, can I get down to 5 or 10, genres between these things. So this is one area where I use the Hamming distance, right? So I took each word in the vocabulary, and I said, do these two descriptions share a word? And I add up the number of words they share. And so you can't read any of this stuff, but here I think are all the black metal bands, here are all the death metal bands, here's something else, and then within this giant thing, there are a bunch of other different subgenres. But if you look more carefully, you can see each of these subgenres in the hierarchical place. Do you have a question?
I do have a question.
Okay.
The bands that you were using, are these like, what level, I guess, of like popularity or recognizability we're using? Or is there something
This is a database of every metal band
okay.
that I think, including garage bands or whatever.
Okay.
Yeah. Sorry, go ahead.
Should you penalize the bands that use names that contain, or describe their own genre with like very many words? Because they're like more likely.
Yeah, that's a great point. One of the things that when I was doing this, right, is deciding what type of words should be in the vocabulary. And like, we're going to talk about text analysis later, but maybe I would like to use some metric like TF-IDF or whatever to say, oh, my vocabulary is only going to contain these 50 most frequently used terms to describe a band. So that's a kind of data, yeah, that's a great question. Other questions? Marcel.
How useful is it for us to predict very small subgenres of metal, and does your model kind of account for that? Like, does it just allow us to classify maybe bigger subgenres as opposed to tiny subgenres that might not mean anything in predicting other kinds of metal bands in a different data set?
Yeah, so I think what you're kind of getting is like an out of sample question.
Right.
Right, yeah, I think that's something you need to be very clear with this type of algorithm. Again, we're not really talking about out of sample prediction as much for unsupervised learning as we are for supervised learning, but Marcel brought this up with me yesterday that like maybe what you want to do is find your clusters and data that you really trust, right? You're like, this is the data I know that I'm interested in, find how these data are clustered, and we might want to apply those clusters to a new data set that we don't know as well, but we don't want it to influence how the clusters are generated. I'll get back to this. One more, yeah, Jake.
I'm wondering, this sounds like kind of an analysis of the dispersive construction of the band's genre, but I'm wondering if you can link it with other data about some music aficionados or critics that look at the actual content of the music and how it's aesthetically different, and if there's some external validity to these different categories that the bands themselves are constructing.
So I don't want to get too much into this particular project, but since you're interested, yeah, I look at this data set of 120,000 bands, and then I go look at other online communities like Spotify, Last.fm, and try and look at external validity of this one. I do want to go back though and point out, because people are interested in text, and we're going to talk about text analysis later, one of the most common, who's heard of topic modeling? Okay, so a good portion of you. So like one of the most common text analysis models is called topic modeling. And it's, if you hadn't learned about machine learning, you would just say, I'm doing topic modeling. But really what you're doing is an unsupervised learning task, right? So you can think about what we're doing here as the centroids, or even maybe my hierarchical clusters, as latent variables, right? We're finding some latent variables here, or dimensionality reduction. And that's exactly what topics are, right? So in topic modeling, we have a bunch of documents, and we are assigning them to topics. Basically, we say that this document belongs to this topic, and this document belongs to this topic. There are some differences between how I've represented it here, but you can imagine that each of these data points is a document, and these centroids are topics. And there are some differences, like a topic model is a mixture model, so a data point could be involved in multiple clusters. And we don't compute distances. We have a complicated system based on word occurrence, co-occurrence. But this is the general idea behind topic models. It's a similar approach. Cool. Any other questions? Okay, I'm going to keep going. Okay, so something else I talked about was dimensionality reduction, right? And I mentioned that already. Like, these things can be thought of as, clusters can be thought of as latent variables. Maybe I want to do an approach where I do that very explicitly. So principal components analysis is one pretty straightforward way that I do dimensionality reduction. And so principal components analysis, the idea is that I want to reduce my feature space, or my covariate space, to a lower dimensional space such that it captures the variance, the covariance, the linear co-occurrence of my different features. So technically what's going on is you take the variance covariance matrix and you do an eigenvector decomposition or an SVD decomposition, and you end up in a space that's one dimension smaller than you initially started. But it's not just that the space is one dimension smaller, it's that each of these dimensions, each of these axes in the space is capturing a dimension of linear correlation in your data. So this probably sounds very confusing, but if I arrange these eigenvalues, I can get the largest eigenvalue will correspond with the dimension where most of the correlation in my data occurs. The second largest will be the second largest, the third largest, etc. So if I look at my data here where I'm taking the first two principal components, right? This is an example of how I would use principal components to do some exploratory data analysis, see how my data is structured. I have the first two principal components, and let's say that this principal component accounts for 70% of the linear variation in my data, right? And this principal component accounts for 30% of the linear variation in my data. And in practice, you'll see that it's only the first 5 or 10 that have a meaningful amount of variation in your data. But you might see, this is maybe not clear here, but you might see if you look at these principal components, there are clear groups, in your data, how that's structured. So why would you want to do this? This would be A, just to get a feel of what your data looks like, or B, again, you want to get down to a latent features, latent variables, and we could use the first 10 principal components in our regression model or in our supervised learning model later, so that we don't have to use 50 different variables. And we can be confident that these latent variables capture that correlation, that linear data that we're using in, say, an OLS model, because that's how this process works. So I imagine that was kind of confusing, but questions? Yes?
Okay, so I have a quick question. What if there's an important nonlinear relationship in the data? What happens?
Yeah, great question. That's not captured by, what's your name also?
Hi,
Hi, I'm Bernie. Yeah, that's also not captured here, right? So that's a great point, right? So this is only going to be able to see linear correlations, linear relationships. You had a question? No.
No,
Oh, okay, cool. Great. So there's another approach that if you want to capture nonlinear relationships called TISNE, T-distributed stochastic neighbor embedding, which is great for visualizing data. But one of the nice things about PCA is it's very computationally cheap, it's fast, and it's deterministic. So you will always get the same principal components. And that's not the case for t-SNE, but it can be useful to visualize your data after you're done with everything, because it will capture nonlinear relationships. Great question. Okay, anything else? There are no stupid questions. No? Okay, great. Okay, so now let's talk about supervised learning. So yeah, I guess I want to repeat, like, why, you're like, Bernie, unsupervised learning sounds amazing. Why don't we just do that all the time? And I'd say unsupervised learning is really amazing. And I think a lot of the stuff happening now in computational social science, the earliest place that people are starting to explore is, how can I use unsupervised learning? How can I do interesting clustering things? So I think Chris Bale even had a paper in ASR very recently, which is doing some type of I don't know, Tianjin, you were telling me about this. Give us an example of unsupervised learning in sociology.
Well, so I talked about the Chris Bale paper to you, but I think maybe a better, more intuitive example is there's a paper by Blas-Variance Tradeoff in Population Development Review, which looks at clusters of immigrants. So there are a lot of diverging migration theories. Like, some say that immigrants migrate because they want to maximize their income. Some say that immigrants migrate to minimize risk in their households. And so basically, Blas-Variance has this data from the Mexican Migration Project, which contains information on the immigrant's gender, previous migration experience, all of these pre-migration covariates, and then she clusters and finds these, 4 distinct clusters of immigrants. Maybe the first cluster are, male heads of households who migrated in the 90s, who, wanted to maximize their income. And the second cluster are, female migrants who, have certain kinds of jobs. And basically, she applied these distinct groups of migrants to these distinct migration theories.
So yeah, it's cool. One of the things I didn't talk about is there are ways to evaluate the robustness of your clusters. If you're interested in any of these algorithms, you can talk to me about that. But getting back to it, it's like, why don't we just do supervised learning all the time? The reality is that supervised learning models really just aren't as powerful as supervised learning models. And a lot of the really exciting, I'm sure you guys have heard of deep learning. I can talk about it a little bit after this, but I think I'm going to have an opportunity to talk about it a little bit on Friday. But like, the exciting stuff happening in machine learning is really supervised learning problems. So how does supervised learning work, right? Supervised learning says, the idea is that we have, we're trying to train the algorithm to learn something that we want it to learn, not to discover some clusters, but maybe we have the clusters. And so we have a bunch of covariates, and we say, for each data point where we have those covariates, this is in cluster A, and this one is in cluster B, and here are 200 examples of the clusters I want you to replicate. And then we train the algorithm to do very good at identifying those types of relationships. And we give it new data that it's never seen before, it can then predict the labels. So they don't have to be clusters. I don't want to give you the impression that we're just doing clustering. These are labels. These are some type of outcome. And this outcome can be a classification label, like a category, or it can be a continuous outcome, which is regression. When we talk about linear regression, we're predicting a continuous outcome, and this is the same type of thing. And so someone brought this up, maybe it was you, and I want to talk about this because I think it's important. So I do think that there's a philosophical difference between how we approach things in machine learning and how we approach things in traditional statistics. Traditional statistics theory is built on this idea that we have representative samples, right? We have some set of data, and the assumption is that the sample we have is representative of this population, or we can do some transformations of it to make it representative of this population. But then we do inference on that sample, and by deduction, we can then generalize about the population, right? That's the idea. We use all our data because we know that it's a representative sample, and this is telling us something about the population. So the validity, the burden of validity in statistics comes on you having good data, having a good representative sample, right? The validity in machine learning, and supervised machine learning, does not come on saying, I have great data. It comes from saying, if I make predictions in this data set, does it generalize to other data sets? Can I make predictions in data that I've never seen before as a way to evaluate whether my model has validity? And I think Duncan Watts, who I think is a speaker in the main site, but we are not going to broadcast him, but he has a great paper about we should be thinking about this more abstractly in how we approach social science, right? That we, at least in sociology, I feel that we often claim we have a sample, we say something about our population, but then we have a theory that it shows that whatever empirical analysis we did explains everything, right? And if you really believe that it explains everything, you should be able to show in another sample that you have validity and that your theory and your model generalize. So I think that's something, even when you're not doing machine learning, I think that's something that you can think about as like, maybe I should be approaching social science and thinking about like how well it can generalize, because I also think that's how we make cumulative progress in science in general. So, okay, digression over. We have two types of outcomes, right? Regression outcomes, continuous outcomes, and classification outcomes. Right. Okay, any questions before I move on? Because this is, yeah. Go ahead.
Not really a question, I guess more like a comment about what you're just saying about prioritizing prediction and inference, but I think in terms of CS, they are like sort of moving toward the idea that like you can't use it. You do some amount of representation in your data. So for instance, facial recognition, they're finding that like on certain races or genders, it doesn't work as well because they've used pictures of all like white men in their data sets.
Right.
So there is some level of importance to how representative your data set is, depending what you want it to generalize to.
Great, thank you. Yeah. Anybody else?
My question is kind of similar. When giving the model training examples, should they be the most exemplar, or should they be like a randomly selected set? Imagine if you classify cats and dogs, but you have some like half cat, half dogs. Can you give it?
Yeah.
Half cat, half dog?
Yeah. This is a great question. Maybe you want to talk more about that, but I think it varies, right? And it varies. So we'll talk a little bit about, in general, like how do we make a trade-off between doing really good in our training and how well we can generalize to external data. And I think some of that depends on the algorithm, and some of that depends on your task, right? So yeah, I think that's a very important idea in machine learning, is not maybe what types of examples do I give it, but which I think is an important question, but I guess what I'm going to talk about is more pragmatically, how can I evaluate whether it's doing a good job generalizing to what I'm interested in or not. Yeah. Does anyone else want to weigh in on that though?
Well, where do we draw the line then? Because we don't want to run into the problem of overfit, right? So we don't is there an iterative way of including more variation over time so that it's very predictive for one thing, and then over time we can train the algorithm to do better with external research problems?
I'm not going to talk as much about that, but there's a whole approach in machine learning called online learning, right? And online learning is exactly that. We start with a model that's trained in something, and we continually give it new examples so that it stays relevant to whatever outcome you're doing. But, yeah.
So building on John's point, I confronted this problem in trying to apply machine learning methods to my text data, that oftentimes there's this ambiguity in terms of classification, and then I feel like just resorting to qualitative methods. But I'm wondering, when you confront the issue of ambiguity in your data where it cannot be clear, when do you throw in the towel? And is there a way to kind of measure ambiguity in terms of the half
So I do think, getting back to your comment, I guess I was dismissive. I said a lot of the data that you're feeding the algorithm is maybe not good. But I do think it's very good to be clear about, to a supervised learning algorithm, this is what I want you to learn. right? So, like, unless you want to identify half cats, half dogs, John, then I think it would be very clear to give it, like, these are very clear examples of cats, and these are very clear examples of dogs. And then you can see how well it's doing on those types of examples. Go ahead, Marcel.
Yeah, just to echo on this, like, this is where supervised learning is a little bit more beneficial than maybe unsupervised learning. So if you're thinking about text, right, the difference between the word liberal in the sense of left-wing policies versus the word liberal in the sort of traditional Enlightenment sense where there's less government intervention, like that might be something that an unsupervised topic model might not be able to make a distinction. It's just going to see those words and then put them all together and clump them in the same topic. And that might not be the sort of relevant distinction that you want to make or classify. And supervised learning can kind of help where if you were trying to maybe get a set of coders that had a very principled set of rules to make a distinction between the two definitions of liberal, and then you put that in a model, you train the data, and then you use that the model to do out-of-sample predictions, then you can kind of resolve that question. And so I think that maybe the issue of ambiguity can be resolved with a very principled way of classifying what you want to classify, and you know, using supervised learning methods to kind of implement it.
Yeah. So I think being clear about what you're training the algorithm, and like the reality is garbage in, garbage out, right? If you're not giving it good training examples, it's not going to learn what you want it to learn. Go ahead.
Yes, I was wondering if there is any minimum number of training examples you can give to algorithm in order to ensure the quality of prediction?
Yeah, so that's a great question. It depends on the algorithm you're using, and you know the types of assumptions it makes, and how much data and practice it needs. So this gets to pragmatically, like, we need a empirical way of evaluating how well it's doing, and we can then see if it's doing a good job on the training sample we feed it, and if it's not doing a good job at making predictions, it's possible we need more data. You know, that may be the case. You know, but we need to evaluate performance to decide whether that's a possibility.
Ernie?
Yeah.
I think also about the data quality and the exemplar question, you don't want actually too good of exemplars from my experience, because then it can't generalize to new examples that don't fit that perfect example. And if you think about like a child learning like red and blue, you don't want just like one shade of red and one shade of blue. You want the possibilities of all the blue so that when it sees turquoise, it can still, the child can still learn blue. So I think that actually it's almost counterintuitive where you do want a little bit of noise, maybe.
So we'll formalize this idea more formally. This is like, the questions you guys are asking are like the fundamental question in supervised learning. So, Marcel.
Yeah, but again, I want to push back because like I think you were just talking about like having all this data and like being able to do a lot with it, but this is where the importance of theory kind of comes into play. It's like you really need to know the questions that you're trying to answer, what exactly you're trying to predict, and what it means substantively in order for things to make sense and to not get things that are a little bit weird and just may not necessarily conform to pretty strong priors or make sense theoretically.
Anybody else? Okay. So yeah, regression, paths, and classification. Okay, so how does, what is a supervised learning? How would I go about a supervised learning analysis compared to a traditional statistical analysis? The first thing is to partition my data. I'll talk about that in a second, but we need to have a training set and really a cross-validation set, which we're going to use to evaluate the model. And then we have a testing set. And the testing set in machine learning is sacred. We do not touch the testing set until our model is completely formalized. And like this would be, if you were to use the testing set to train your model, your claims of having any external validity are baloney, right? So this would be equivalent to p-hacking, maybe, would be kind of analogous to use your testing set to train your. So it's very important to set aside a significant portion of your data, and this can get to your issue of do I have enough training data, but in practice you need 10% to 50% of your data to be set aside for testing. That depends on how much data you have in general, but I'll get to that in a sec. So I have a testing set, a cross-validation set, and a training set. I'm going to train the algorithm on the training set. And what the algorithm is doing is it's trying to optimize some loss function. We talked about minimizing distance. It's a similar idea. Like, it is trying to make a prediction, and it is trying to minimize some function that captures how well it's making predictions. We got to this idea already, but we don't want it to overfit, right? And so there are approaches we can take, even though its objective is to optimize the loss function to do as good as the prediction as it can, we might add some other approaches or parameters or whatever, or things to prevent it from learning the training data so well that it can't generalize to a new data set. And this is called regularization, so I'll talk about this also. Then we get to cross-validation. So this is how we evaluate whether the trained model is doing well and whether we need to fiddle with any knobs, right? So the machine learning part, the machine has a lot of parameters that it is going to optimize on its own. But there may be additional parameters which are called hyperparameters, which the human has to choose what those values are. So after we train it on the training set, we'll go to the cross-validation set, we'll evaluate performance, and we can tweak any knobs that we need to tweak and go back to training and try and train again. And once we're happy with all the knob tweaking, then, and we're saying the model is done, we're not going to change anything else, then we apply it to the test set. Oscar.
Can you give an example of what the what you're suggesting?
I will, when I go through these different algorithms, I will give examples of hyperparameters. Yeah. Okay, and then the last thing is it's done, apply to the test set. Okay, so just to be clear, I'm going to try, as like an organizational thing, I will try and stay with this structure as we go through it. Any questions here? Hopefully they'll be resolved as we keep going. So, okay. So, this is trying to give you a visualization of what I was saying. We have our whole sample. We're going to cut it down into a training set and a testing set. Within the training data, and for that matter, just to be clear for you, the testing set does not have to be labeled with outcomes, right? That's kind of the distinction we're making. The training data has to be labeled with outcomes. You have to be able to tell the algorithm, this is what you should learn. And the testing data is the data where you don't know the outcomes and you want to make predictions. Okay, within the training set though, you need to,
Sorry. So would it be naive to consider, so say I have a whole sample and I observe, and I select out the testing set based on the fact that I don't observe the outcome variable of interest. If I have a latent model in which like sensor data is censored because of some reason, that will bias my estimate of, because a testing set is actually not the same as a training set.
Yeah.
It's like people that have a lower income, people that have some other feature that, right?
Yeah.
Oh, right.
Yeah, that will be an issue. And so,
so how's it usually done?
How do we combat that? Yeah, I think that's a real challenge for machine learning. I think regularization is one way that we can try and get a model that will hopefully learn the things that we want to learn and still be able to generalize to new data. Thinking about your particular case, if there are features that are not going to exist in the testing set, then it's very intuitive that we should not include those features in training. Because the worst thing that could happen is that the algorithm makes decisions based exclusively on the features that we don't have, and then it sucks, right, when you get to testing. I would need to think more about that if anyone else wants to weigh in on that.
I think this is also very similar to what Sarah mentioned earlier about the algorithms that are trained on data sets that are not diverse, and then you try to like use those algorithms on stuff in the real world, and it doesn't work.
Right.
So like that's basically the issue that you have there.
Yeah, I think so. That's like, I think computer scientists just like invented these methods, and then they were like, oh, this is great, but then like in practice now they're kind of realizing that like the actual data that you put into it is also important.
Yeah, I think I just want to
Garbage in, garbage out.
echo everything. Yeah, garbage in and garbage out. Like the data, like echo all the things that people have said is that the data is probably the most important aspect of having a model that can predict well in the testing set, as opposed to like all the fancy methods. And you'll see that in some of the examples that we'll show you is that, you know, like if you change, like if you use boosted trees versus a logistic regression, you're not going to get a lot of performance out on a bad data set versus a good data set.
Yeah. It doesn't matter how fancy your model is if your data is not going to tell you what. If your data doesn't contain information, then there's nothing to learn.
Separate question. You mentioned that the testing set doesn't have your variable of interest, or like the dependent variable?
You don't have to know the dependent variable.
Right, so I don't understand that, because isn't the whole point of testing set is to evaluate your model?
That's a great question. No, that's the point of the cross-validation set. It's for you to evaluate how well your model is working. The testing set, and maybe we shouldn't call it a testing set. Maybe we should call it, the out-of-sample set or whatever. That's really what we're using to, that's our goal. That's our task of interest, right? We don't know the outcome, and we're, I don't know, you can say imputing, but predicting the outcome in this data.
But we won't know the outcome of the testing set, right?
We don't know the outcomes in the testing
I
set.
think typically though, like at least for CS papers, you would keep a sample of your labeled data as a testing set, and you want, like, they typically report statistics on that.
Okay.
Right, so you can say, oh, my model works 95%.
Yeah.
on the
Great,
test.
yeah, that's great, yeah. Great.
But how is it p-hacking if you have, like, if you touch the testing set at all?
So, I think, again, our goal is to, our primary metric of is our machine learning is whether we are predicting out of sample, right? Whether our thing can generalize to new data. And if we are training our algorithm to do well on the data that we're interested in, we can never make the claim that it's generalizing. We just claim that it trained on a broader, more diverse training set.
Yeah, and just to clarify, like training and testing sets, like there's a lot of like competitions that are out there where you actually are able to see the outcomes for the testing set or the final classes for the testing set. But what we're really talking about are like real world applications, right? Where you develop an algorithm, you develop a model, and you have some data, and you're trying to predict some classes, and you really don't know what are the classes in a different corpus of data, and you're trying to figure that out in an automated fashion. But like in practice, you're trying to produce new data via some sort of classification method, and you're really not going to know what the outcome is in the testing set in most contexts.
Or the application set, maybe is really what we should be calling it. Yeah.
Are the proportions divided into training and testing set, are those, is it like 30, 70?
It really depends. If you have 1,000 data points, then maybe you need to have a much larger percentage of your sample for cross-validation. Or if you have 10,000 data points and you really only need 1,000 of them for cross-validation, then maybe it can shift between whether you need 10 or 50%. And yeah, I don't have an answer of what is the right number. I don't have an answer. But you need a significant portion of your data, such that like you would believe that the cross-validation set is representative of the data as a whole and not biased because it's so small.
And on top of that, I mean, that depends on the heterogeneity of the population that you're looking at, or the variance in the population, right? So like, if you have a data set of 1 million and you sample 10,000 units, right? That might work if the population is more homogeneous, because you're basically going to get all the same kinds of people in the 10,000 that are representative of the other, like 1 million minus 10,000, right? I can't do math. But if it's a heterogeneous population, you still might miss units. Even though you have a large sample, given that there's like a population of 1 million. And so this problem is also dependent upon the variance in the population, or in the variance in the whole data set that you're trying to look at.
And variance in a broad sense, not just putting a variance. Yeah.
Related to the variance question, obviously in a lot of our social data, there's a lot of minorities. And it can be really hard to get like certain cells that you're looking at matrix of different like covariates. So like, is there a way to make an intervention in terms of weighting, overweighting, or obviously you might even want to oversample certain minority groups when you're actually doing the data collection, if you're collecting data. Or is there ways to like post-stratify before you go into this process?
Yeah, absolutely. I would say yes. The answer is yes. Those are both things you can do, especially for classification issues like the cat and dog thing. You might do that quite a bit if we have, we're interested in a rare class, like 5% of our data is dogs, and we want to tell the difference between cat and dogs, we should definitely overrepresent dogs, so that we can, so that it really learns that. And again, I think a lot of these things will be clear how we can talk about them once I get to formalize it in the next couple slides. But this is an issue in classification that we're going to talk about. But that was not to discourage any more questions. Anyone have a question? Okay. Okay, so what's represented here is like, I think John asked like, can I, like what percentage of my data do I need to actually reserve for cross-validation? This is just showing one technique called k-folds cross-validation for me to pump as much value as I can out of the cross-validation set, so I have to use as little of it as possible. So basically the idea is that I take, let's say I have 5-fold or 10, let's say this is 5-fold cross-validation. So I say this is my training set, this is my testing set. I'm going to take only 20%, instead of saying 50% of the training data is for cross-validation, I'll take 20% each time and I'll train it with a different training set and I'll see how it does. And then I'll do a different 20% the next time and I'll see how it does. And then a different 20%, so that I'm constantly shuffling in what's in the cross-validation set and what's in the training set to kind of augment my data, to get like a more robust data set where I'm evaluating cross-validation. And maybe I can then average the cross-validation, the performance metrics across these different data sets. So that might be a way for me to use 10% of my data for cross-validation instead of 50%. Okay? You don't need to know that, but if you ever come across k-folds cross-validation. Okay, so going back here, really what the algorithm is doing is optimizing some loss function, right? And the most obvious loss function for regression, which is really actually what OLS is doing, is the mean squared error. Or, this is, like I said, this idea would keep coming up. This is also called the L2 loss, right? And so I have y hat here as my predicted outcome. Y is the true value. I take the difference, I square it, and I average the results. So that's the mean squared error. The L1 loss, analogous to what we saw before, is the absolute value of the differences. And why would we want to use different loss functions? In general, this will be the main loss function you use, but maybe you would use what did I say? Mean absolute error? I think that's right. That's what MA is. I think it's mean absolute error. And why would we want to use it? Well, maybe we have crazy outliers in our data, and we don't, this is the equivalent to using the mean, and this is the equivalent to using the median, right? The mean will be a better metric on a larger sample, but maybe will be less robust outliers. There are all other types of losses that you could use that may be appropriate in different contexts. In kernel methods, like support vector machines, use a hinge loss. So again, this is something you can look into. In classification, the most common loss function is the log loss. And one of the things I didn't say is that even though they're different tasks, there's very few models that are exclusively classification models or exclusively regression models. And that's because what happens is for classification tasks, we take a regression model and we tell it to predict the probability of classes. So it's actually a continuous outcome, and then we say, here's some decision threshold, like logistic regression. If it's above 0.5, then I'm saying it belongs to this class. It's below 0.5, it belongs to this class. So we could use accuracy, and I'm going to talk a bit why we wouldn't want to use accuracy, but something better than just saying how accurately does it apply to each class is using the log loss, which takes not just whether it accurately predicted that class, but how confident it was that it was in that class to evaluate the performance. But other ones we're going to talk this afternoon, maybe briefly about entropy and about Gini impurity as well.
Gini impurity.
Yeah. Okay. Questions? Okay. All right. So we've already gotten to this discussion quite a bit, but the bias-variance trade-off and overfitting. So in statistical learning theory, we talk about bias and variance, and this is not the same bias that you are used to talking about in, not quite the same, but related to the bias that you're probably knowledgeable about in traditional statistical models, right? So the bias here is when we talk about bias, we're talking about bias in our training data versus variance, generalizability in our test data set. And I want to make sure I get this right. I might get it wrong, so anyone please jump in and correct me. But when we talk about bias, we are saying for a single data point that might be included in multiple different training sets with other examples, how accurately can we predict that in the training set, right? So this is how well can we fit the training data? How well can we do in the training data? So that's something we obviously want to do. Like, that is the goal of the algorithm. Like, it needs to learn the training data. If it's not learning the training data, it's not useful. But we also needed to generalize, right? We also needed to generalize to the test set. And that's what variance means. We want to know, for a single datum in the test set, how wild are its predictions for that single datum when that datum is included in different other test sets. So that would be like, basically like when it generalizes to data it's never seen before, does it make the correct prediction over and over, or is there a lot of variance there? Is that clear? Okay, so this is a trade-off. You can't do both. You cannot have the lowest bias, least biased model that also has the lowest variance. If you are learning the training data really well, you will, by definition, learn things about the training data that are idiosyncratic to the training data and will not be able to generalize to a new data set. That's the reality. And there's a nice derivation, which you might want to look at, of the mean squared error, of the L2 error, that shows how it can be decomposed into loss due to error due to variance, error due to bias, and some irreducible error. So if you're interested in that, you can look that up. But traditionally, the main thing that we can change to make this trade-off, like whether we care about bias more or variance more, or is it going to do better at bias or variance, is to manipulate the complexity of the model, right? So this is Jacquet's great fake polynomial OLS regression, but this is what we would be talking about, right? So a really complex low bias model here will have lots of parameters. This has a number of polynomial parameters, and it does a freaking awesome job at predicting the training set, right? It gets maybe not every, but almost every training data point. But then when we give it the green dots, which are the testing data, it's crap, right? It doesn't get any of these things at all, and it's not good. And so when we give it a much simpler model, a quadratic model here, it actually does decently. It has higher bias, but maybe not terrible bias in the training data, but does much, much lower variance. It does a pretty good job at extrapolating to new data. Okay. Is that clear? Okay, so this is, like one way that we could do regularization is to include fewer parameters, right? Not over-parameterize our model. What am I talking about? Yes, regularization. Right, so how can we regulate? So first thing is like, what is the best solution to having a low bias, low variance model? Or how do we, what would be the best way to guarantee we have a low bias, low variance model? This is kind of a trick question. It's not about the model. Okay, the correct answer is have really great data and lots of it, right? You have a huge data set that really is representative of the entire possible population of things you're interested in. And you train that, and you get a huge number of training examples, and it does a great job on all the test examples because it's fantastic data and it's enormous, right? That's the best solution to having a low bias, low variance model. If we can't do that, though, we can do some things to our model to prevent it from overfitting. This is what we call overfitting the training data. You probably heard that term. I think one of you even used it, right? So one thing that's common in deep learning and you could use is to just stop training early. Like, don't let your model get the lowest possible mean squared error that it possibly can. Just stop the parameters from training. or stop specific parameters from training, maybe. Another approach you can take is to use a bunch of different models. Maybe they're all from the same, algorithm, or maybe they're a variety of different algorithms. I am going to actually talk about some specific algorithms in a bit. But you take all those algorithms, and they all kind of learn slightly different things, and then you ask them to vote together on the outcome, like your final prediction. So this is called ensemble learning. And then another thing that I'm going to talk about, I think, because Marcel is going to show an example, but it's common, very common in machine learning, is to add complexity constraints on your loss function. And so, or sometimes called like shrinkage parameters or penalties or whatever. So the most common, and I did this late last night and it's not good. But the most common two would be an L1 or an L2 penalty, right? So, and so we'll talk about L2 first, right? I said these things would keep coming up. This is called ridge regression, right? So if it's applied to an OLS model and not a boosting tree or a neural network, it's called ridge regression. But the concept is the same. It's also called the L2 norm or L2 penalty or whatever. And the idea here is that we have the thing that we're actually trying to estimate, but we also have some penalty on the size of the parameters, right? So we say the sum of the parameters together cannot be larger than some number, constraints. 55, I don't know what the number is, right? This would be an example of a hyperparameter. It's basically we're tuning that number. In practice, we're actually tuning a multiplier by that whatever some of the parameters are. But that's really what we're doing. We're saying, is this quantity smaller than some number? So I'm going to try and show you briefly how this would work. And so let's think about this again in a context you're all probably familiar with, which would be linear regression, right? So if I have a bunch of correlated parameters, am I going to get good coefficient estimates? No. The answer is no. If my parameters are highly correlated, if they are perfectly multicollinear, regression will fail, right? But if they're partially more collinear, you will get estimates, but if they're predicting the same thing, maybe one time this parameter could be huge, beta 1 could be huge, and beta 2 could be small. And another time you run the model, beta 2 could be huge and beta 1 could be small, right? Because they're telling you the same information, it's hard to partition what amount of the variation is due to one parameter and what amount of variation is due to another. Does that make sense? Right? That's like a common issue. So let's see if we can draw that for a two-parameter regression. I'm just going to call them beta 1 and beta 2 because one of them would be the intercept.
Is there a black one?
Yeah.
Is it hard to see here?
Yeah, it's hard to see.
Okay. Thank you. Oh boy.
Remember, there's spray there if you want to erase.
Okay. How are we doing on time?
11:37.
We have
Okay.
Yeah. You might want to write on
Okay.
the right side.
I'm going to do this very quickly then,
Right on the right side.
so I can get through to other things.
It's better, I guess.
Okay, so we can imagine that there are a variety of solutions. If some of these can be high and some of these can be low, there's a variety of solutions that could occur. This could be the correct solution, where we have exactly one value, or we could have one be bigger and one be smaller, or one be bigger and one be smaller. And at the same time, for this constraint here, where we have this penalty here, we can think about whatever the size of the number is, whether it's 55 or whatever, these can be the solutions on the total sum of values. Basically, what ridge regression is going to do is you're going to find some point that's on both of these, probably it will be a point that's on the edge of both, that will be such that your parameters are small. So to avoid inflating huge parameters because they're multicollinear, this type of penalty is going to force your parameters to be smaller than they would otherwise. And choosing how big the penalty is going to be is something that you'd have to do via cross-validation. Okay? And so the L1 norm looks like this. Whatever, I can't erase it, screw it. The L1 norm looks like a diamond as opposed to a circle. And this is useful because if you are on this space, on the diamond, often you'll end up here, as opposed to on the edge of the diamond. You'll end up on a corner of the diamond. And that's great because it means that if your parameter is not telling you anything, it will shrink to 0. It will disappear. So this is, a useful model because it can even reduce the number of extraneous parameters that aren't providing you information in the model. So this is called lasso regression. Okay, people have questions about that, or can I move on? I think I kind of want to plow ahead because I feel like we actually have a lot of good conceptual stuff, and now I'm just going to cram crap in there, and you can talk to me afterwards. How about that? Okay. Okay, so the other thing we talked about, this got me to cross-validation, right? So hyperparameters, this is where we would tune hyperparameters. When we talk about trees later this afternoon, for these ensemble learning algorithms, it's like, how many trees do I want to use? Do I want to use 5 trees? Do I want to use 1,000 trees in my ensemble? How big should my ensemble be? This is an example of regularization, the lambda parameter. In trees, it might be like, how deep should I let my tree grow? How big should the leaves in my tree be? So this is what I want to tune during cross-validation. I want to evaluate the performance of the training set in the cross-validation set to see how well it's doing and tune hyperparameters so I can get it to do as well as possible. So how do I do that? For regression algorithms, I'd still look at the mean squared error for the most part, or whatever metric that I used that I was interested in training, because that's really what I'm trying to do here is I want to use continuous output. For classification, there's a lot of different, it's a little bit more complicated, and there's a couple things that we can look at. So you might be asking, and Marcel will talk about, actually I'll let Marcel talk about this more, but we're going to do a classification test this afternoon, and not a regression task, even though you're all probably familiar with regression tasks, and it might be more common. And Marcel will talk about contexts in social science where we might want to use classification. Great. So classification metrics. We could look at the accuracy. Like, is it predicting class 1 85% of the time, and 85%, it's 85% correct in its predictions of class 1. Or rather, it's 85% overall correct, right? If I have class 1 and class 2, 85% of the time it gets them in the correct class. And we'll talk about why that's not really a good metric, or at least it's a reductive metric that loses a lot of nuance in how well your model is performing. So really what we're interested in is precision versus recall. And we'll talk about that. But you're probably familiar from statistics with type 1 and type 2 error. And that's really what we're talking about here, precision and recall. And then these are different ways to summarize precision and recall. So why not accuracy, right? Let's say that we are trying to train a model and we have 995 cat examples and 5 dog examples. The model will, like maybe the best model we have could just predict cat 100% of the time. Like it literally doesn't learn anything. But that would be a great model for our training set because we have so few dog examples. Does that make sense? And that's why accuracy isn't capturing particularly something like particularly recall. So, we talk about type 1 error, or the false positive rate, and type 2 error, the false negative rate. And in classification supervised learning, we summarize it in these two metrics, precision and recall, right? So precision is how many of the total positives do I actually predict as positive, right? So that's like, I don't know, people always teach us breast cancer and they talk about type 1 and 2, type 2 error. So let's talk about breast cancer, right? So how many of the people who actually have breast cancer are we predicting as having breast cancer? That's the precision, right? And then, sorry, that's not correct. That's the recall, right? The recall is, of all the people who truly have breast cancer, how many of them am I getting, right? So that's what we have here. These are all the people who actually, all the positives, the total positives, and we're saying what percentage of these total positives are we capturing, right? That's the recall. As opposed to the precision, which is of all the things that I predicted to be positive, which one of those are correct? I'll give you a second to just look at it and sink it in, because it's, yeah.
There will also be materials that will be uploaded to the Slack that give definitions for what exactly precision, recall, and accuracy are. Also, some other metrics for determining accuracy, like the F2 student.
Yeah, so I'll go through those quickly so that we can move on. Yeah, but you can think about cases where you might care about precision or recall more than the other. So if I'm predicting breast cancer, maybe I'm wrong about this, but from my perspective, I would want to have very high recall. I would want to get as many of the people who actually do have breast cancer as possible, even if it means I'm going to have low precision and I erroneously predict a lot of people who are negative having breast cancer, right? But what if I am saying I am the, what's it called at the airport? What are the people at the airport called?
TSA.
TSA. And I want to say, Oscar, you're a terrorist, you know? Like, if I'm going to classify Oscar as a terrorist, I want to be very damn sure that, like, Oscar is truly a terrorist before I call him a terrorist, right? So I want to have a very precise algorithm. Maybe, I don't know, maybe someone would actually say, no, Bernie, we want to catch all the people, and yeah, just the current, like, we could do racial profiling to have a really high recall, algorithm. But from my perspective, we would want to have a very precise algorithm, right? We don't want to accuse anyone of being a terrorist unless it's very clear that they're a terrorist. I don't know, maybe there's a better example for that, but I should have thought about this in advance. All right, keep going. Right, so Marcel's going to talk about this in the afternoon. But for binary classifier, we can, visualize precision, the precision versus recall trade-off using a receiver operating curve. So I think this would be precision in general-ish here and recall-ish here, although it's not exactly what we're doing. And you want to have an algorithm that is up here, basically has an L shape. That means that when it has high precision, it also has high recall, right? And you want to have, like when you have high recall, you always want to have high precision. So that's why you want to have an L shape. Really, ideally, you would want a straight line, right, across the top. But we can't do this, right? It's a trade-off, kind of like the Blas-Variance Tradeoff. And so it often looks like a curve. And if we want to do something reductive, we could do the integral of this curve to come up with what's called the area under the curve. As kind of a composite summary of how well your classifier is doing. Really, you want to look at precision and recall and think about which one you care about. But if you want to say, I only want one number, this would be the number. This does not generalize well to when you have multiple classes, and that's when you would represent a confusion matrix. And Marcel is going to show you a confusion matrix this afternoon, but the idea is you just see how many things along the diagonal are correctly classified and how many ones on the off diagonal are incorrectly classified. That's kind of an idea to see how well your classifiers are. Okay. What time is it?
47.
Oh, I'm doing great. Okay, let's take questions. No, it's clear. Okay, Jake.
What the TP and FP rate are again?
So true positive rate,
Oh, true
false
positive,
positive
okay.
rate.
And what does AUC stand for?
AUC stands for area under the curve, which is not super clear because it's specifically the area under this curve, but that's what people call it. So if my thing was like this, if I had a straight line across the top where always I have high precision, no matter what, I think this is recall, I think this is correct, but no matter what the recall is, I have high precision, then the AUC would be 1. So this is a number between 0 and 1. And the higher it is, the better. But again, like, it's hard to look at this for multiple classes. And there are other metrics that kind of, if you need, for a multi-class problem, you need to summarize other metrics. Marcel will talk about some of these this afternoon, but like F1 is something you'll commonly see in papers for a classifier to see how well it's doing. So we're going to do a classification task this afternoon. Oh, I should get going, actually. I forgot I have to do the tree stuff.
Yeah, we have to
Okay.
do tree stuff.
Okay, so what are some supervised learning algorithms that you could encounter? Generalized linear models, right? You know all of these. All of these algorithms can be used as machine learning algorithms, right? OLS can be used as a regression algorithm. A logit can be used for either regression or classification, depending on what you're interested in, right? You could say, I want to predict the probability that someone would go to college, which is a regression problem, or I want to predict yes or no whether someone goes to college, which is a classification. Kernel methods, so this is like support vector machines. I'll try and go really quickly through it. Artificial neural networks, which are not commonly used in social science right now. That's going to change in 5 years. I want to talk about more about that. Hopefully I'll get a chance to talk about that later this week. Today we're going to talk about tree maze methods. Did you need to add something?
No.
Okay, really quickly, what does an SVM do? An SVM is something that is trying to find the boundary between two different classes by finding some nonlinear line that separates the two classes and maximizes the margin between each class, points in each class on that side of the line. And computationally, the way that this works is it uses something called the kernel trick. So a kernel is like a matrix operation that transforms these data points to a high dimensional space, and where basically that's how we allow like nonlinear lines to be drawn, nonlinear boundaries to be developed. Because if we're in a linear space, the only thing is a straight line. But if we're in 3,000 dimensions, we can come up with some complicated hyperplane to divide the two classes. And so the kernel trick allows us to do this computationally efficiently by computing the inner product between these things, between these different classes, between different data points, which is like akin to the distance in the space, even though we don't need to know with the kernel trick how to actually project these points into the space. But if you're not interested in any of that, just know that it's trying to find this boundary between these two classes and can come up with a complex nonlinear function to do that. And relatively non-parametric. I'm not going to talk about neural networks. I think I should keep going. Okay, if I have time, I'll come back to this. Okay, so decision trees. This is what we're going to do this evening. Compared to SVMs or neural networks, part of the reason neural networks are not used is because they're what are called black box models. It's very opaque how they work. This is where I think causal inference is going to be huge, and we're going to talk about it later this week, because that would be a way to do social scientific inference instead of just machine learning with some model I have no idea what it's doing, like a neural network. But decision trees are where we would say a white box algorithm, because we can see how the algorithm is making decisions. And I think this makes it appealing for social science, and it's very simple to understand. It's a very simple algorithm, which is why you're going to do it manually this afternoon. So, who knows what this game is?
Guess who?
Yeah.
Guess Who, correct. And I found Guess Who from Pulp Fiction. So these are Pulp Fiction characters. So in Guess Who, if you're not familiar with Guess Who, it's a childhood game which is the same as 20 questions, right? So I am trying to do a classification task essentially where I'm like, who is this person, right? And like the most inefficient way to do this, where you say, oh yeah, Bernie, like this could really work, is I could say, is it Jules, But then, like most of the time, I'm going to be wrong, right? So that's, I guess if you're a gambler, that's a good approach, but it's not a good approach in expectation. The best approach in expectation would be to say, start with the most general question and get down to the smallest group of possible people. So the most general question would be like, is this person male? I mean, Pulp Fiction, actually, there are very few female characters. But is this person male, theoretically, partitions your data set, you automatically excluded 50% of people, right? So that is the most efficient question to ask. And that's what a decision tree classifier is doing. It's playing 20 questions, asking the most efficient question until it comes up with leaves in the tree that all belong to one class. Or for a regression task, have a minimum distance to their mean. But we can talk about that. It's easier to understand for classification. So in Wikipedia, if I look up decision trees, which I totally did to prepare this talk, here's a decision tree about whether you survive on the Titanic or not, right? So, like I said, the first question would be, is this male? Then, are you young? If you're young, you're probably going to die. Because you can't swim, I guess. I'm speculating. But anyway, we go through the features that we have, the covariates, and we select if it's a categorical feature, we would just say yes or no. But if it's a continuous feature, we say the feature and we pick some threshold that allows us to ask the maximally efficient question. And we go through that until we've categorized everybody, or we apply some regularization constraints, right? But theoretically, these trees could go very deep until we get leaves where everybody is in the same class. Okay, is everybody following? Okay. So, what is the loss function for decision trees? There's two loss functions, but the one that we think is the easiest to understand and is already used in social science is like the Gini coefficient, which is used for inequality in social science, but it's really, we can use it to look at the inequality between classes, right? So if a class is, all right, let me make sure I get this right. If a class, 5 minutes, I think that's fine, right? You'll just have to go this afternoon. And,
yeah, that'll be fine.
Yeah, okay. Okay, Marcel will talk about this afternoon. Basically, if a class is maximally equal, right, we have 0.5 and 0.5, the Gini coefficient would be small. And if we have a class that's very unequal, or a group of data that's very unequal, and we have 0.1 and 0.9, we multiply those together, you would have a very high Gini coefficient. So,
yeah, I mean, the basic idea here is that if the Gini coefficient's larger, that means there's more difference, right? If the Gini coefficient's smaller, that means that there's less difference. And you want to find the set of features that has the smallest Gini coefficient, because that's going to produce branches that are relatively homogeneous. And that's what you want to do with the trees. You want to produce increasingly homogeneous branches at the end of the day.
Great. Okay, so this is the decision tree algorithm which you are going to implement on paper this afternoon with a very simple example. So, okay, what happens to the first step?
It's calculate the Gini. Yeah.
Oh yeah, okay. So we want to identify the most impure feature and split on that feature, right? Actually, is that correct?
It should be the inverse.
Yeah, it should be the inverse,
Yes.
right?
Yes.
Yeah, okay. We want to identify the most pure feature, or the most, the feature that will allow us to split the data into two sets that are of relatively equal size, right? We don't want to gamble down, you know, is it Jules? Is it John Travolta's character? Like, keep gambling, right? We want the feature that will split into equally different size. So, and if it's a regression thing, we might have to choose a threshold on which to divide it. So then we remove that feature from the data set and we split on the next feature. And this is how we would like follow the branch down the tree, and we recursively keep doing that until everything, there's no more impurity, we have, you know, homogeneous leaves, or we run out of features, or there's no more data, or alternatively, which is what you will actually do in practice, is you want to regularize so that it will generalize to new data by pruning the tree in somehow. So you either limit the size of, if you say the leaves have to be at least 100 units large, or the tree can only be 3 levels deep, or whatever, you know, but there are different ways to prune it so that it generalizes to data better. Okay. The last thing I'm going to talk about is like, this is a greedy algorithm. How much time do I have?
2 minutes.
2 minutes. Okay, whatever.
So quick. Just brief.
Yeah, briefly. Okay, so this is a greedy algorithm. And by that we mean that it makes the same decisions every time, and it makes decisions based only on local context. So once it has made a decision, it doesn't look at the impurity of the entire data set. It just looks at the impurity of the data that it has already split upon. Okay, so that's why it's greedy. It's not making the maximally optimal choice. It's making a locally optimal choice. And that's bad, because that will prevent you from generalizing. It makes it much faster, but it will prevent you from generalizing. And it's also deterministic, so we'll do the same thing every time. That's appealing, maybe from a social science context. But to do that, because we're prone to overfitting, we can basically do various things to make our thing more robust. So one thing we can do is bootstrap our data. Does anyone not know what bootstrapping means? Okay, great. So we can bootstrap our data and run 1,000 trees, right? And then vote on the best prediction for each unit based across those 1,000 data sets. Okay, that's bootstrapping. Or bagging. It's called bagging. Bootstrap aggregating. So the other thing we can do is called feature bagging, right? Where at each set in the tree, at each decision the tree gets to make, you say, tree, you can't consider is it male or female? Because every tree is going to ask, is it male or female, right? And we want to have more variance in how trees make decisions so that they can better generalize to other data sets where not, like most people are going to be male, and that's not a useful question to ask, right? So we say you can't ask whether it's male or female in this case. And at each split, we randomly decide that there's a certain number of covariates that can't ask about. Okay, and these are called random forests. Okay, so when you have both bagging, which is bootstrap aggregating, and feature bagging, and you have both of these combined, and then you create 1,000 trees and you have them vote on predictions, you take the average of their prediction, that's called a random forest. The other very powerful approach that we're going to talk about this afternoon is called boosting. And in practice, I think boosting algorithms are the most performant classifiers that are not deep learning classifiers. They're opaque to see how they work, but they're the best. You can't say there's any one best algorithm because you have to try them all, right? That's how machine learning works. But I think in general, these are some of the best. And these take like the error of the entire data set, and they create what are called weak learner trees. So instead of saying we're going to have 1,000 trees that all predict the entire data set, a boosting algorithm will make a very deep tree that only focuses on one specific area of the data set. And then it will compute how much error that tree is for predicting the rest of the data set. And it says, okay, I'll add one more tree that focuses on the center of that error, right? And so it keeps adding more trees that focus on very specific narrow parts of the data set. So it's a very broad and average approach, which is random forest, versus like very narrow and very specialized approach, which is boosting. And the way that it does that, you add these trees one at a time, and you compute the total gradient of the error, and then that's how you decide where you want to add the next tree. Okay.
Yeah, just one last really quick thing about trees is that, like the kind of regular tree model doesn't do very well in terms of prediction. The key thing is to understand these ensemble methods like boosting and random forest, or to learn them on your own, because that's where you get a lot of power in terms of predictive accuracy.
Okay. Does anyone want to hear me pontificate about neural networks for 2 minutes?
Yes.
Yeah.
Okay. Okay. I'm cutting into your lunch hour. But. Okay. So, great. So artificial neural networks. So these are algorithms that have been around for a very, very long time. People were doing real research with neural networks in the 80s and I think probably the 70s. But they were not very good for a long time because they're very expensive to train. And there's issues with them overfitting. And so figuring out how to regularize them was a challenge. But, and furthermore, coming up with unique ways to parameterize them in unique network architectures is something that has only happened in the past 10 years. And so starting around 2011, 2012, these issues got sorted out. People were discovering, not discovering, but these new architectures were taking off. And when we talk about deep learning, starting in 2011, 2012, these algorithms started to outperform pretty much every other machine learning classifier. They're very expensive to train and they require huge amounts of data, which is why they aren't probably being used in social science yet. But eventually, that problem will be solved because you will get more data and there will be pre-trained models that you can download and will somehow be able to, you'll be able to look at your data set using a pre-trained model. But these are being used for all types of tasks, for text analysis tasks. Maybe Alina will talk a little bit about that. No? Okay. Okay. Maybe for regression, for classification, all types of tasks. So the way that this works is the simplest. So when I talk about these, I'm talking about what are called feed-forward networks or multi-layer perceptrons. There are other architectures that have, when we talk about deep learning, it's usually using more complicated architectures. But the simplest architecture is a multi-layer perceptron. And really, the simplest architecture is a perceptron, right? And so a perceptron.
Bernie, it's hard to see that.
Green is actually easier to see.
Okay, what about red maybe?
It might also just be better over right,
Yeah.
where it's a little bit less
To the
messy.
right, yeah.
Here?
You should always write on the right.
Okay, can anyone see this?
I'll use the green marker, it's easier to see the color.
Okay, I think I'm just going to go to this and simplify this. Okay, so real quickly, like in a neural network, let's imagine that there's only one of these output nodes, and we're just looking at this part, right? So in a neural network, we have our input data, and that's each of these nodes. This is like simulating the human brain. And we have some output node, right? And each of these input nodes are connected by weights to the output node, right? And this output node activates if it reaches a certain threshold. So it has some function, like a sigmoid function, or a logistic function is it's not the most common one anymore, but it was the first one to be developed. And you'd say, if you get above 0.5, fire, output. And so this model by itself is logistic regression, right? These weights are the parameters of logistic regression. It takes 3 different inputs. Imagine we don't see this. Each of these inputs is connected to an outcome. And we weight these parameters so that we do the best job of regressing the outcome, let's say. So this would be like a graphical representation of logistic regression, right? Is that clear? It's hard without drawing. Okay, but these are the betas. These lines are the betas. This is your input data. This is an outcome. And this thing has a logistic, thingy that says like fire if you reach a threshold. Okay? What makes neural networks powerful is that they have what are called hidden layers, right? And so they don't just have straight from the inputs to the outputs, but they have these hidden layers here that all the weights connect to each hidden layer node, and then all the hidden layer nodes connect to the next hidden layer, so you can have multiple hidden layers. And each of these nodes does the same thing as what I said the output node is. Right? Each of them has a logistic function, and they only fire if they get greater than 0.5. And like I said, these things didn't take off for practical reasons, but there is a theorem that shows that if you have a hidden layer of infinite size, you can approximate any convex nonlinear function. So it's a very powerful model. Like logistic regression is essentially, it's a linear model, right? These can learn any nonlinear function. So that's why they're very powerful. And the way that they get trained is something called the backpropagation algorithm. And basically, what that does is it takes the error and it uses calculus's chain rule to backpropagate the error in each weight all the way back to the beginning weights, assigning a proportional amount of error to update these parameters, these betas, in each layer, according to how much they contributed to the total error. That's the simple neural network. Neural networks in 2 minutes. Okay, thank you.
Okay, so unfortunately, the neural networks have eaten into your lunchtime, and we actually have a speaker that will live streaming from Princeton at 1 p.m. So try to be back here at like 5 to 1. I'll be sending out like 2 suggestions for food like in a near vicinity. But you obviously you can like go wherever you choose. Let me just send this out. So there's gonna be links on the Slack, and we'll be back in like 1 minute.
Yeah.
Yes.
Oh, just south of this. You know what it's